So we are in sort of the last little gasp of group theory, if you will. I'm going to talk about, we're talking about composition, series, and solvability. I'm going to give you, this is basically kind of a language thing, right? Acquaint you with some of the terminology here. That's the big takeaway from this. Definitions. Three, I think. I'm going to define several types of series. Number one, a central series. It's a series of groups. It's a sequence of groups. It starts at one, which is normal in G1, which is normal in G2, normal in Gn minus 1. So it is just an ascending chain of subgroups, and it satisfies one more thing, such that look at this commutator group. This is contained in GK for all relevant values of K. Now, so what this means is when you take, and remember what this is, maybe I'll write this over here. In fact, I'll do this generally. This is the group generated by commutators of the form HK, where H is in H, K is in K. So take all commutators that look like this, and that's what they generate. So here, in this notation here, your commutator would look like commutator GX, where G is in G and X is in this bit. And each one of these commutators should drop you down to the next level. A central series is a sequence of groups that satisfies this. These are all normal. This commutator group drops you down to the previous one. I don't claim that every group has a central series. In fact, we call a group with a central series a special name. Series. Say G is nilpotent. In a certain sense, this is a generalization of an abelian group. Number two, an upper central series of G is one that looks like this. An upper central series G is a sequence of groups this form here. I'll take the sequence of the form so I'm going to define the first one to be Z0. It's going to be the identity. That one is normal in Z1. normal in C2, normal in CK. Now I'm going to tell you how we define dk plus 1. Okay, so I define Z0 to be 1, right? And that's where the ball starts. CK is the set of X and G, or ZK plus 1 is a set of X, G, such that the commutator XG commutator XG is in CK. Like notice, of course, all these groups are in G, right? Because CK plus 1 is defined to be all X and G. So no matter what, all these things are contained in the G that we start with, right? Let me explore this one a little bit. What would Z1 be? Let's kind of think about this a little bit. This is X and G such that for all G and G, XG is in Z0, right? Just by the definition. But what is Z0? It's 1, right? So this is the set of X in G such that for all G and G, the commutator XG equals 1, right? Well, let's take this apart a little further. This is the set of X and G such that for all G and G, XG equals GX. This is equivalent to the commutator of XG being 1. Can somebody describe what Z1 is?
Center.
It's the center. So Z2, you just take this up a notch. Such that for all G and G, commutator XG is in the center of G. So now X is not necessarily in the center, but its commutator for every G and G is in the center, and so forth. And this actually may be the center again, or it may be a little bit bigger, right? So these things grow as you go along, right? But at some point, it may get stuck, right? If Cn equals G for some n, and G is nilpotent. So there's two ways that we can define nilpotent there. Number one, from the central series, and number two, from this upper central series as well. It's not clear, I don't think at this juncture that these two are, yes.
So over here, you say essential series, and having essential series implies the last of the sequence is equal to G. Then over here, you say an upper essential series, but then the last symbol is a subgroup symbol, not an equality symbol. So I'm just a little confused. Is every upper essential series essential series?
No, they're different.
They're different.
They're
Okay.
different. They're different, but they have the same end to the means, if you will,
Yes,
right?
okay.
So if G actually has a central series, which is when we build this way, then it's nilpotent. And if we on the other hand, if building this upper central series, so, in fact, actually, let's look at what happens here. So let me clarify this. This is a central series in general, right? This is what we define it. And what do we say here? What do we need? We need normality. We've got it here. And what else do we need? We need the commutator with G and GK plus 1 to be contained in the previous one, right? But here, what we do is we build the specific. So an upper central series is a central series, right? But nobody said that a general central series has to be that particular one, right? So maybe that's a little.
Yeah.
Okay, you can also do what's called a lower central series, and we're also going to start this way. And then again, we're going to look at a particular lower central series. So in the ones that we've done before, or the ones we did with the central series, we started at the identity and we built bigger groups and we asked ourselves, does this eventually end up at whatever the group is? We can also kind of go the top-down approach. 3. A lower central series. Of G or for G, if you will, is a sequence of groups, of subgroups of G. Here, we're gonna define this. The top, we want G1 to be normal. G2 to be normal in this. So now we're going from the top down, if you will. And I'm going to insist where GK plus 1 is the common. So we build the next group this way. So in other words, to get G1, it's just G0 commutator with itself. To get G2, that's G0 commutator with G1. To get G3, it's G0 commutator G2, and so forth and so on. And this gives a descending thing. Again, it may get stuck. There may be some point where it stabilizes. Right? It might, well, if G is finite, it must stabilize. But the question is does it get all the way down to the identity? And the derived series for G, you've seen this one. And it's actually a variant on the previous one. Is given by G equal where G1, G0 is defined to be G. G1 is the commutator subgroup. And GK plus 1 is GK. You actually messed with, in the current homework, you're mucking around a bit with aspects of this particular series. If Gn is the identity, or some in natural numbers, we say G is solvable. Okay. Okay, yes.
So for this, I know for this one, like Z1 has to be the center. For this one, do we have it, how do we get G1? Is it just any normal subgroup?
In number three.
In number three, yeah.
Oh, right. So G1 here,
Or that formula holds for G1?
yes,
Okay,
because what G1 is, so let me clarify, G1 here, I'm sorry, G sub 1 is by definition G0, right? But G is G0, so this is G0, G0. So actually, this is, again, the commutator subgroup. Okay, so this so G1, this is defined by the commutator. So G1, that's when K equals 0, is the commutator subgroup of G and G0. The G0 equals G. So this one right here is the commutator subgroup. So this G1 is the same thing as this, right? They're the same. After that, they might split off. This one I expect to be a little bit smaller, right? Because this one is the commutator of G1 with itself. This is the commutator of G2 with itself, and so forth. This one is the commutator of this and this. G3 is this and this. So it might be, so these might be a little bit bigger than ones.
over there, you say, so you're saying G1 is equivalent to G0?
No, what I'm saying is by definition,
All right.
here when K equals 1,
Yeah.
this is G1 is G comma G0.
Oh, okay.
So that's not a 1, that's a comma.
Oh, got it. Yeah, that makes sense. Thank you.
Okay, yes.
I'm still really confused about the solvable definition. So I'm not really even sure like what to ask. Cause like what does the line above it mean?
Right, so here's what this means. Start with your group G, right? That's its commutator subgroup. Okay with that?
G1 is the commutator subgroup of G0.
That is correct. G and G0 are the same, they're synonymous, right? G1 is the commutator subgroup. You okay with that?
Yeah.
Okay, so now you've got a smaller group, G1, the commutator subgroup. Now take its commutator subgroup. There's G2, right? Now you've got a possibly smaller group. Now take its commutator subgroup. Now you got G3. Keep doing this crap. If you eventually get down to the identity, it's solvable.
Okay.
But you might not. You might get stuck at some point and you have like G10 and you take its commutator subgroup and you get G10 back. Well, now you're stuck, right? And it's not solvable if G10 is not the identity. Does that make sense?
Yeah.
Yes.
One more question. Is the derived series essential series or no?
No, well, the derived series,
No.
yeah, so the lower central series is bigger because we're defining how this is built by taking the commutator of this and the next one. This is of the same ilk, if you will, but it's actually something a little different. It is the derived series is a particular series that involves the successive commutator. Okay, I'm going to define another type of series that now we're going to focus on with respect to, I did say that we're going to use this to talk about, what is the importance of simple groups, for example. So I'm going to give you a particular series here. Let G be a group. Let G be a series of the form, the sequence of groups and these are successively normal groups. One equals G0, which is normal in G1, which is normal in G2. So this time it's ascending. Normal GK, normal GK plus 1, GN, just I'll put G. Where each by the way, let me point something out here. Notice that G0 is normal in G1. G1 is normal in G2, G2 is normal in G3, etc. Remember, normal is not transitive. Just because G0 is normal here, which I require, does not mean that G0 is normal in G2 or in G in particular, right? It's just the only thing you know is normal the next one. But that's all I need here because notice GK is normal in the next one. And so I can actually mod out, right? Because GK is a normal subgroup of GK1. Suppose that we have the sequence of normal subgroups and we have the quotient being simple. This is called a composition series. So all you need for a composition series is just a sequence of groups, each one normal in the next, and you want each quotient to be simple, right? So that quotient group is a simple group in the sense that it's got no normal subgroups other than itself and the identity. In this case, we call each successive quotient, GK plus 1 mod GK, a composition factor. Okay, so that's just definition time here. Let me give you, and this is the important, I've got a couple other theorems in the notes that I'm gonna skip over because you're doing them in your homework, so you've got the next two theorems. I'm gonna jump on to kind of the previous two theorems I'm skipping over and just talk about solvability, which are exercises. I claim, well, first, let me make the observation. If G is simple, it has a composition series. So I want to look at a couple of examples of composition series. If G is simple, if it's a simple group, it's got a composition series. Can anybody tell me what it is?
The identity is in the kernel.
Okay, right. This is very silly, is it not? Notice 1 is normal in G always, and G mod the identity is isomorphic to G. So any simple group has a composition series in a rather natural sense, right? So, note. By the way, this is true in more generality than I'm gonna write it here, but I'll keep it simple. If G is a finite group, G as a composition series. Did anybody, see why this is true?
Shouldn't it be true for every group, because in every group, the identity one is normal to the entire group.
I think you might have problems. You got an infinite, or it's potentially okay. It's not so clear. I mean, for example, take the rational numbers. So why would it be true for a finite group? Okay. Prove this. Already shown that any finite simple group, in fact, it doesn't matter if it's finite, we proved up here that any simple has a composition series. Everybody agree with that? Okay. Let's go by induction on the order of G. We'll say the order of G is n. By the way, notice off the top of my head, I know that the first three base cases are true, right? The order of G is one, it's the identity group. It's clearly got a composition series just itself. 2 and 3 are both prime. So those two, if the order of G is either 2 or 3, it's simple. And we go back here. In fact, the first problem I ever run into is 4, but I've already got base cases covered. Everybody okay with it? Okay. So suppose holds for all groups of order less than or equal now suppose the order of G is n plus 1. Anybody see how we might proceed here?
But in our definition, 8.1.4, we have that modulo, the previous one. As long as that's simple, it's a constant series, but we have by induction that it's simple.
Okay. So, good. If G simple, then done. Far remarkable, right? If my group of order n plus 1 is simple, I'm done. If not, then G has a normal subgroup. In not the identity. Normal in G, but not equal to G. So it's a proper subgroup that's more than the identity, but less than the whole group, right? How does that help? Well, since the order of n is less than or equal to m, then n has a composition series. Right? So one normal and two normal in n. So m. Yes.
I'm a little confused about the implication of since the order of n is less than or equal to n, then that has to follow then.
By induction.
Okay,
We're assuming that
Oh, yeah, yeah.
for all groups were.
yes, okay.
So I've got to compensate. So I can climb the ladder up to n, right? That's essentially. How do I go the rest of the way? I think the third isomorphism theorem might come in handy. Notice that. Also note that the order of G mod n is less than the order of G. So induction applies as well. So G mod n has a composition series. And I'll write it this way. One normal in let me call this G1 mod n, normal in G2 mod n, normal in GT mod n, which is G. Now, what I've done here without saying anything is I'm actually using the third isomorphism theorem, because this chain of subgroups, these have to be subgroups of G mod n, right? But the third isomorphism theorem says, hey, what do subgroups of G mod n look like? They're subgroups of G containing n, right? Everybody okay with that?
Yeah, so what you're saying is that's how we can guarantee it's always mod n and not like some weird.
That's exactly right. What we're doing is we're creating this sequence of subgroups of this thing, right? So I could write some random stuff here, but really, here's what I know. All the subgroups of this look like subgroups of G that contain n, right? And so there's no loss in generality of me writing it this. So each GI is between N and G. Right? And in fact, since GI mod N is normal in GI plus 1 mod N, this means that GI is normal in GI plus 1. Because, right, these are successively normal. And again, the third isomorphism theorem says that each GI is successively normal at G1. So now I'm going to glue this together. Let me build something longer. 1 is normal in M1, normal in M2, normal in M, which is N. And now I am going to do this. Right? Let me try to convince you that this works, right? What do we need? We need each of these to be successively normal, right? Well, we're okay here because N has a composition series, so each Ni is normal in the next one. And we also know that Ni plus one mod Ni is simple. Right?
And
So we're
from this one, this like little bit over here.
from this right here. So I'm gonna verify this, so I verified this part of it. I'm gonna verify this part, and then I'm gonna verify where they connect, right? Where you jump from the N's to the G's, right? How about these here? Well, also G, Gi plus one mod N mod Gi mod N is simple as well, because each successive quotient here is simple, right? But what is this isomorphic to?
Gi plus one mod Gi.
Good. Again, the third isomorphism theorem. So now these successive, we've remarked that each of these is normal in the previous one by the third isomorphism theorem, and the successive quotients are simple. Finally, N is normal in G1. Because again, this is a subgroup, so N has to be normal in G1. And I guess I really need to know that this is simple. And G1, see, I'll make the jump here. Right. Okay, so I did make the jump here from the N level to the T level. Right. So G has a composition series. And we're done by induction. Yes.
So what motivated you to do N normal in G1 as opposed to just you have over there one? Like why do we have this tail of N? So why can't we just put a one and be done? You know?
Well, because what we're doing here is these N's are these groups and these are the homomorphic images. So remember what we're doing here is we're modding out by N.
Okay.
So a translation of this, you might think of, this is really super sloppy, okay? I probably shouldn't even record this, I'll be embarrassed. But think of multiplying through by the N. N is contained in G1, it's contained in G2, and so forth, right?
Okay.
And that really kind of does make sense because of the third isomorphism theorem, because this one here, really, in this context, is N mod N,
Okay.
right? And so really, this is the smallest, N is the, N equals N. So this quotient right here is the identity. And this G1 contains N. See, these things usually aren't comparable, right? These are subgroups of G and these are quotients, right? Just like if you look, the even integers is a subgroup of the integers, agreed? But the quotient group, Z mod 2, you can't compare that to the integers, right? And so that's kind of what's going on here. The trick of this is here we're passing from this right here back to the groups right here. And this is where we're strapping things together with the third isomorphism theorem, because every subgroup of this corresponds to a subgroup, namely GI, that is between N and G, right? And the successive normality also follows by the third isomorphism theorem. Does that make a little bit of sense?
Yeah.
Okay, other questions? Yes.
why do we need all those additional G's, G1 through GT, if we're just trying to inductively prove the next G?
Because you gotta get all the way up to G, right? So what we have here is we have N is a subgroup of G. We built the train up to here, right? Because we knew that that sucker had a composition series. The question is, how do we get from N all the way up to G? And the problem here is we don't know how to use the induction. I had to use G mod N, right? Because that drops the order down. And I know that G mod N has order less than or equal to M, so it's got a composition series. But this is a different group. This isn't G, it's a homomorphic image of G. So I've got to translate back, right? It doesn't make any sense to put G1 mod N, G2 mod N, because they're not even comparable. What I'm doing is I'm basically pulling the, if you use sloppy terminology, numerator groups out, and the third isomorphism theorem lets us do this, right? And so now I've got this chain here. They're all successively normal. Check this, check this, check the connection. And then they're successful, the successive quotients are in fact simple.
Wouldn't the orders of those G1s through GT minus 1, they would have to be between, what we defined,
Yeah.
N and M, right?
That is correct. The order of G1 is a little bit bigger than N, I would expect. And the order of G2 is a little bit bigger than G1s and so forth and so on. And you got to climb the ladder all the way up to G.
But we have that M is immediately the next step from. Did we not have that go? So what I mean is it holds before that. Is that not our ends that we're getting there?
It holds before this, and it holds for any proper subgroup, but you've got to show you can get all the way to the tops, right? Because the order of this is M plus 1, and the inductive hypothesis doesn't apply. That's why I had to tear it apart into these two smaller pieces.
The thing is that N that we're defining, because if it's not simple, it's to have some N.
That's
We
right.
don't have that guarantee that N is order A. It's just somewhere before.
Right. That's right.
Thank you.
Okay, other questions? Okay, so here's all the hullabaloo about composition theory series. Theorem 817. This is called the Jordan-Holder theorem. Theorem 817. This is the Jordan. Any two composition series for a group G have the same length and composition factors. Let me point out if it exists, if it actually has a composition series, then any two of them have the same length and composition factors. And when I say composite, the same up to isomorphism. And you can use these oftentimes you can use these composition series to stitch together a group. Let me give you an example or two. Let me start with something simpler. let me explore composition series for Z6, right? Here's a couple of interesting groups here, subgroups. Notice Z6 has those two subgroups, right? The first one's isomorphic to Z3 and the second's isomorphic to Z2. Composition series, how can I get that? Well, by the way, I don't have to worry about normality here, do I? Because Z6 is abelian, so every subgroup's normal. So I don't have to, that's not even something on my radar. See, I guess I'll just define this. I'm going to call this length 2. I'm going to start by counting at 0, 0, 1, 2. Okay. What are the composition factors? This mod this. Everybody agree with that? And Z6 mod Z3, which is isomorphic to what? G2. Now, this is not unique in a fallacy sense. Here's another way I think. Oh, normal signs anyway. Notice this is a different composition series, right? Of course, they both end up at Z6, but here I've got a different one in the middle. Do I agree with that? So the length here is again 2, as the Jordan-Holder theorem would predict. The composition factors Z2 and Z3. Notice they're in a different order, right? But they're the same. So again, we've got the same length and the same composition factors. Everybody okay with that? Here's an example. How about S3? S3 is not simple. Can anybody tell me what the normal subgroup is? Other than the identity and the whole thing. Like there's that normal subgroup of order 3. This one was very similar to the previous one. So here I have length 2, composition factors, let's see, N, which is isomorphic to Z3, and S3 mod N, which is isomorphic to Z2. Notice I get the same length in composition factors as I did from Z6, right? However, it is impossible for me to get it in the other order, right? Well, yeah, this would be the other order here. It's impossible for me to do that. Basically, the cyclic group of order 6 is stitched together by taking a direct product of Z2 and Z3, whereas S3 semi-direct product. Here's another one. This one's short too. S5 has A5. It's normal in S5. and A5 separately. So a composition series for this would be 1 A5 S5. So the length, again, 2, and the factors, composition factors, are A5 and Z2. Okay. Any questions on any? Well, put that in your pipe and smoke it. We will come back on Friday and we'll start talking about brains. Yes.
Just a curiosity thing, when we're talking about composition factors, how much do we care about order for calculus?
Oh, well, you should probably put them in the order. I mean, well, we put series, but not great.